Let's look at SSTs again in the context of this surface heat flux and salinity flux, freshwater flux, and buoyancy flux. The annual mean, the seasonal cycles, DJF and JJA. We have seen the animation of this before. You cannot see it clearly here, but the upwelling here, for example, is maximum during the boreal summer months because the ITCZ goes north, the southeasterly trades get stronger, and the warm pool moves north and south with the sun. So you can see it is more in the southern hemisphere here, pulled further south, and it's all mostly in the northern hemisphere here in the boreal summer months. Associated with that are these currents, the north equatorial and south equatorial currents, the equatorial counter currents, and on the equator you have westward currents, and you have the Kuroshio. There is a similar picture, of course, for the Atlantic Ocean with monsoonal differences in the Indian Ocean. We have also talked before about how the Indian Ocean remains warm throughout the year because of the various processes like deep convection here creating subsidence over here and warming during some part of the year, and the monsoonal circulation coming with weaker winds in the northern Bay of Bengal part, upwelling happening along the Somali coast, and so on. You can also see the SSTs moving north-south here in the southern hemisphere, in the northern hemisphere. This warm pool actually is called the western hemisphere warm pool because the Gulf of Mexico gets really warm, and the warm waters get pulled all the way up here where the ITCZ is, and you can see the warm water here, and this becomes part of the hurricane season, etc. So we have to combine the net heat fluxes, the freshwater fluxes, the mixed layer physics, and the currents to produce the distribution of sea surface temperatures. Obviously, there is a strong relation between the ITCZ, SPCZ, SACZ, and so on, and the sea surface temperatures, because convergence and rising motion in the atmosphere, deep convections, always happen over warm waters. There is a threshold of about 28 degrees centigrade that is required for atmospheric convection to happen, even though you will not hear much about just how large the patch of that SST has to be. And of course, the details about how the atmosphere responds to warming begin to get a little bit more complicated, because Indian Ocean, for example, can get warmer than 28 degrees centigrade because of the subsidence, and there can be no convection because there is subsidence from the top, and so on. Okay, so interpretation of the sea surface temperature distributions can then be looked at in terms of the balances. So here is the incoming solar energy up here at 342 watts per meter squared, and the latent heat loss is going to increase almost exponentially with temperature, because the specific humidity with Clausius-Clapeyron is going to increase. Of course, there is a linear wind dependence as well. Obviously, winds become very critical in the subtropical gyre. There is the long wave, which increases with temperature, obviously sigma T to the fourth, and sensible heat also increases, but you can see that they are relatively small compared to the latent heat flux. So this is where the balance happens, depending on where the net loss or net gain of the heat flux happens. So that's kind of the equilibrium sea surface temperature if only one-dimensional balance was happening and heat fluxes were determining the SST. Obviously, things are not that simple. Here is the sensible heat again, latent heat flux again. In the polar latitudes, temperatures are very low. As we saw, latent heat flux can be low, but alpha T varies strongly with temperature, as we saw, and also with pressure. This dependence is called a thermal thermobaric effect. So the increase of alpha T with depth is called thermobaric. Temperature and pressure. Baric, barometer, is pressure, right? So that can produce destabilization of the water column if the displacement of a fluid parcel because of gravity waves or turbulence or convection. Deep water formation is also convection in the ocean. We've been talking about convection in the atmosphere, but when instability is caused in the ocean with heavy waters on top, buoyancy loss, then that collapse of water is also convection, right? If they are sufficiently large, then you can produce instabilities in the ocean just by this thermobaric effect. Just to remind ourselves again, the mixed layer physics remains very critical, especially at low latitudes, and then we have the Ekman pumping happening. So the heat balance cannot be done without this entrainment term, which is related to Ekman pumping. Even though we cannot compute it on the equator because there is a F in the denominator, we know that there is Ekman divergence on the equator, which lifts the thermocline up, brings the cold waters close to the surface, but makes this gradient stronger, in which case you either need a lot of cooling to break through that stratification and entrain colder waters, which happens in the Arabian Sea during the winter, for example, or you need strong winds to produce wind-driven turbulence, which happens in the regions where there is actually upwelling and surface cooling. So the subtle difference you want to understand in the end is that just upwelling doesn't necessarily cool the surface. It increases stratification and brings colder waters to the surface, close to the surface, and enhances the tendency to cool the sea surface temperatures. You need this entrainment, the turbulent kinetic energy, to entrain the cold waters across this strong gradient to cool the surface waters. This has huge consequences for biology as well, because you need nutrients to be entrained into the light zone or the euphotic zone to have biological production in the surface waters. So those are just kind of process details. We will see how these work at higher latitudes so that we can put that in the context of buoyancy loss, convection in the ocean, and deep water formation. Okay, we are kind of running through the thermodynamic processes of the ocean, which are closely related to the dynamics. We can think of wind-driven circulation as, let's say, dynamics, and the buoyancy and heat flux, freshwater flux as thermodynamics, because they change temperatures.